Hello Ravens. Today we're going to be looking at parametric functions and vectors. Starting with our parametric functions, essentially we have xy coordinates that are connected to each other. We're still looking at a Cartesian plane. We're looking at two dimensions only. Except now, rather than having x and y connected to each other through simply a function in terms of x, we have each variable having their own function. And they're tied together by a third variable called a parameter, which is usually shown as t. So if we're looking at an example of that, so you can see here that for any value of t that we put in, you're going to get an x and a y. And if you combine those 2 points, you end up with your Cartesian coordinate. So x and y are still what you're graphing. T will never actually be graphed except to show direction, which I'll demonstrate in a moment. So if we simply want to tackle graphing this, it works much the same way as it would in the past. We just have a third variable to consider. So if you table this out, you have your t, your x of t, and your y of t. And let's pick a few points. So let's say we start with -2, -1, 0, 1, and 2 for t. What this will come out to is we can plug our -2 into our x of t function. That comes out to a -8 plus 4. So you're going to end up with -4 for your x value. And if you do the same with y of t, you're going to take that t, -2, comes out to -8 times 3 halves, and that will come out to -12. So you can repeat this process. So now when we go to graph this, we look at the x and y coordinates. We ignore the t for now. And so here's your function. This can be a little tedious when you're working with very large or complicated parametric functions where x and y are in terms of sometimes of trig functions, very large equations, or fractions. So there is something that makes it a little easier to visualize. Many questions will ask you to eliminate the parameter, and that's referring to the same concept where we're actually going to take y and x, we're going to look at their functions, and we're going to try to eliminate that t variable so that we can say y in terms of x. If we look at this same function and we try to eliminate the parameter, the easiest way is probably just to look at x and say that x of t, which is also just equal to x, minus 4 is equal to t cubed, where we've just moved the 4 over. And now, since y of t is equal to 3 over 2 times t cubed, you can actually just substitute. And you can see that that lines up with what we got. We got about 0, -6 here, which makes sense for our b, and we got our line. So that's where that comes out. This is a good point to mention how t then is graphed. The only indication for t that we put on parametric functions is an arrow that represents the direction the function is going. So as t increases, this function is going up in this direction. It's following that path. So this is a little harder to direct substitute in for, but there's a way to make this far easier, which is take the trig identity of sine squared t plus cosine squared t is equal to 1, and substitute some of this in. So the y, for example, is going to substitute in really easily here. You can just put that in directly. Here you end up with x plus 7 is equal to 7 sine of t, and if you're looking for that sine of t, easy, just divide by 7, you end up with 1 7x plus 1. And so now you have that sine, you need it to be squared, plus y is equal to 1. The last thing we're going to look at as an intro to parametric functions is finding the domain of t. In this case, we can just separate this out. We know that because of this rad t, t should be greater than or equal to 0. We know, since we have a 4 minus t in the denominator, that t cannot equal 4. And from this ln of t, we get that t should be greater than 0. And so combining all these things, it's fairly simple to get out the interval, and there you have that t domain. The first thing we're going to look at is how to take a derivative with the parametric function. We're going to go back to that first example, and like I said earlier, we're going to kind of demonstrate how this is a linear function, and we're also going to show how to find a tangent line to a particular point. So the first thing, when you're looking at trying to take a derivative, for x and y it's fairly simple. You're going to be looking at x prime of t is going to be the equivalent of dx over dt, since it's in terms of t. Same goes for y prime of t. and that's going to be relevant once we try to take the derivative of the whole function, which is going to be dy over dx. And essentially when you're looking at dx over dt, it's just in terms of t, so you can do this just like you would any other derivative. So for dy of dx, essentially what we're looking at, dy over dt all over dx over dt, 9 over 2 t squared over 3t squared. These will cancel out, and this comes out to 3 over 2. And that lines up with our graph from before, that you have a slope of 3 over 2. So this is useful in finding the tangent line, since now you have the slope of the overall function, and you'll have the slope of that tangent line. We'll look real quickly at finding the second derivative, since this is a little more strange. This is actually equivalent to the derivative in terms of dt of your dy dx over dx over dt. This is 0 over that 3t squared, which will come out to always 0. Makes sense, there's no change in concavity. There's no concave up, no concave down for a linear function. So now that we've looked at derivatives, the next thing we're going to look at is integrals and how they work with parametric functions. And there's two main things that we're interested in here. One of them is the arc length, where we're going to slightly modify our original arc length equation, and the area under a curve for a parametric function. For our arc length equation, we originally had where these we actually substituted in d over dx, d over dy, and this is of course a modification of our distance formula. With parametric equations, the difference is that we want this in terms of dt, and these a and b values, rather than standing for x coordinates, are going to be t values. So for parametric functions, this is going to end up equaling, so it's the same idea. And let's say we apply this to that original function, then you can see that we already found the derivatives for these. They'll give you some interval. So in this case, let's look at from 0 to 2 for t. And you can solve with the calculator for these. 14.422, roughly. We can then move to area, where traditionally we've been looking at area as a definite integral of a function, where that's the formula. For a parametric, essentially how you can think of it is this x is now a function, and you can say that x is equal to this function f of t. So you want this in terms of t, which means two things. You're going to plug this in, and you're going to want this dx. Our area is now going to change into a to b. Again, these are in terms of t now, so don't get those mixed up with x coordinates. And you essentially have f of t. Now we don't know what the original f function is, but we do know f of x is equal to y, and that we have a function y that will be represented by some new function g of t with a parameter. So again, let's look at that original parametric function. And here you'll see that if you plug this in, we have the derivative of this. Let's look at that same interval here for t, so that you get this 0, 2, and you have your y of t, 3 over 2 t cubed, and your x prime of t, which is 3t squared, dt, which is equal to 48. So that concludes parametric functions, which means now we're going to move on to vectors. There are a couple of main ways in which we show vectors. So one of them is using these bracket-like symbols. And so what that there represents is you've got an x value of 0, a y value of 2, and a z value of 3. And these x and y coordinates are the same as the Cartesian plane, except now this z is the three-dimensional aspect. And you can also have vectors in this same notation that are functions. So you could have, and now what you're doing is you're essentially, in similar fashion to a parametric equation, you're showing each one of these things is equivalent to the variables. So the other form that we could take upon this, we'll look at the same values here, would be using these special letters. So you've got an I, a J, and a K. These are all respectively tied to a variable. In this case, this would come out to 0, so you would probably just be shown 2J plus 3K. These letters are interesting because they can act as both constants and variables. They don't change, they're not really manipulated, but once we get to adding calculus to some of this, you'll see that when you take derivatives and when you integrate, they act as constants, they don't go away. However, they also can't be combined across each other. So if you have something like another vector that you want to add, let's say you take this vector 0, 2, and 3, and you want to add to it the vector 1, 0, 0. 0i plus 2j plus 3k, and you're adding this new vector in, you just have an I, a 0j, and a 0k. And so you can see that this I is going to, you have one I plus 0 i's, acts almost as if it were a variable, to where you end up with this new vector. It's also important to note that you don't necessarily need to have 3 dimensions when showing a vector. If you had something like this, you're showing an x and a y. So this applies to 1-dimensional, 2-dimensional, and 3-dimensional points and equations. Alright, so from there we're going to move right into the calculus pretty quickly. You have this notation, it's very similar to parametric as I mentioned. If you wanted to take the derivative, let's look at this example here. You take the derivative of this independent of the others, so you get 2t, this becomes 3, and this becomes 1 over t. And so you see that we've now taken this vector here, and we now have a vector that represents its derivative. So some FRQ questions will ask you things like find the velocity vector. And in that case what they're referring to is you'll usually have a position function. You can show that as a vector, and the velocity vector is the derivative of that vector. So it'll be some sort of 2 different functions that represent that 2-dimensional derivative. The same applies for integration. So if I took this here and I wanted to integrate this vector, it would be, and so you see we've taken the integral of each one of these. Important to add, since this is an indefinite integral, you still have to add that plus c, which you can add outside. So like I said, you're not usually going to be graphing 3-dimensionally, but it can be a little disorienting when you're dealing with 3-dimensional vectors, trying to visualize some of that space. One of the ways I like to think about it is when you're dealing with a Cartesian plane, if any coordinate you have, like a comma b, you're looking for the a value on the x, the b value here, and then you're drawing out a line to where they intersect and forming that square. With a 3-dimensional function, if you think of it like adding this 3-dimensional part and you're adding this component, instead what happens is they all triangulate to this new central point. And rather than forming this square, you're forming a pyramid, a 3-dimensional pyramid that goes to a particular intersection point. Alright, so before signing off here, we're going to go over a few common mistakes that you'll want to look out for. One of the main things that can happen here is if they ask you to do this and they ask you to graph, people will forget to put the direction in terms of t, but that t is still in there. And kind of an extension of that is also there's usually a t domain. So if you forget that once you eliminate the parameter, you might get the function of, say, an ellipse. And so if you were to graph it, you see this ellipse here. But if you graph it just from the parametric function, you get something like this instead. And the reason for that might be that there's a domain on t. Always make sure to check that t domain if you're going to graph using y in terms of x. And also make sure to remember that this has direction. Moving on to vectors, if you're taking an indefinite integral of a vector, you always need to add that plus c. And remember that it's a little strange now because that plus c is actually a stand-in for a vector itself.